So combination, the key thing now is the order does not matter. Oh, and this is supposed to be missing that line. So, combination is just a permutation with the, you might want to make a note here. That's all we're doing here is divide out the order. So if you took the permutation and divided out the order, you would get a combination. Now there's some special cases, and you can imagine these with a deck of cards. I have 52 cards. Choose all 52 of them. Good luck. You did it. It's amazing. I did it too. 52, choose 52. How many ways can you do that? One way. Does that make sense? The order doesn't matter. It's like, oh, I still have the same 52 cards. Okay? We've done 52, choose one. Right? 52. Who has never played the game of 52 pickup? Does anyone not play 52? Have you ever played 52 pickup? No? Would you like to play?
Yes, she does. Yes, she does. Yes, she does.
You do this, and you take the cards and you flip them, and they all fly up in the air, and then you have to pick them all. You're good? 52 pickup? Fun card games. Okay. And we also saw this. This is kind of long-winded way of saying the same thing. But n choose n minus r and n choose r are the same thing. Meaning that if I choose 15 cards, oh my goodness, it's like choosing 37 cards. Right? So if they choosing a group of what, much easier if I start with just 10 cards. 2, 3, 4, 5, 9, 10. If I choose a group of 3 from 10, I'm always left with a group of 7. If I make a new group of 3, I make a new group of 7. And so 10 choose 3 is the same as 10 choose 7. And that's what this idea says at the bottom. Yeah, we saw this example in our notes. Exactly why it works. Remember with combinations, whatever this number is, it's going to be on the bottom, and the bottom two numbers add up to the number on top. A very famous application of combinations is poker. Because if you get a poker hand of 5 cards, you're like, oh, man, 10, Jack, Queen, Ace, King. If only they were in the right order, I better fold. And then like someone else would be like, that's a straight, that's good. The order, you can rearrange your cards. You don't have to hide like, oh, now I have a straight. The order doesn't matter. So in poker, and maybe one of the reasons that the game of poker is so intriguing is the number of hands that are possible is 52. Choose 5. And if we do that on our calculator, so 52, math, go over to probability, choose 5 of them, 2,598,000. 960. Almost 2.6 million different poker hands. So you can play poker hands over and over again, and chances of you seeing the same hand again are very unlikely. So here, be ready to be amazed. I'm going to deal out 1, 2, 3, 4, 5. You will probably never, ever see this again in your life. I got the 2 of spades, the 10 of diamonds. I know excitement is rising here. The 6 of hearts, the 5 of spades, and the jack of spades. You You will probably never see this 5-card poker hand again in your life. I guess my chances of getting this exact poker hand is 1 in 2.6 million. But, for those of you that know poker, how good is this hand? It's terrible. It's like the worst hand, basically, possible. I have 5 cards that no pairs, nothing high. It's not very good at all. But the chances of getting that exact hand was 1 in 2.6 million. Okay. For those of you that have played poker or watched on TV, we're going to do some of the math related to it. Very typical exam question is, first of all, it says committee. You're making a group of people, right? It doesn't matter the order. It's going to be the same group of 3 people. I make you into a group. You say, I don't like our group. Okay, well, I'll change it. You first, second, third. Oh, it's the same group of people. Right? You're still frustrated with your group. Order doesn't matter. So committees, order doesn't matter. But we have to make 2 boys and 3 girls on the committee. So we can't choose it all at once. We have 2 decisions that we need to make. We need to choose our boys and choose our girls. And for the boys, it would be 15, since the order doesn't matter, choose 2. And for the girls, it would be 18, choose 3. And because they're decisions, we would multiply these 2 together to get our answer. A group of students must be separated into 3 smaller groups. So 8 people are going to be in group A because it's more work. Group B is a little bit easier, so it's only going to be 5 people. And group C is 7 people. Right? This is a phys ed class, and they're going outside for cleanup day at the Living Prairie Museum. And there's different areas. One area is bigger, so they put 8 people in that group, and so on and so forth. How many ways could this be done? Okay? So, a couple of ways. I think the easiest way is saying, well, we have 3 main decisions. We have to decide who's in group A. Can anybody be in group A? Yes. We have to decide who's in group B. And we have to decide who's in group C. Now, if you decide on group A first, there are 20 students in total. And we need to choose 8 of them to be in group A. Now, once I've done that, why is B not 20, choose 5? 8 of them are already in group A. How many people are left? 12. Okay? So there's 12 people left. Now we have to choose 5 of them. So I chose group A. I say, you guys are in group A. Right? I chose group B. You guys are in group B. Norman's in the back there going, I wonder what group I'm going to be in. Can't wait to find out. And what's going to happen with the last group? Right? Whoever is left is going to be in group C. So this part, 7 choose 7, that's going to be 1. Because at that point, anybody who's left is going to be in group C. Would it have mattered if I mixed things up? Like if I chose group C first, and then chose group A, or B, it doesn't matter, and then A. What if I did the order? Would I get a different answer? Shouldn't, but let's see. But my numbers will be different because this will be 20, choose 7. Now how many people are left? 13. And this would be 13, choose 5. And then I have 8 left, it would be 8, choose 8. That would at least be 1. Now, I'm going to do this above the first one in green. This is going to be 20 factorial over 8 factorial, 12 factorial, right? And the second one is 12 factorial over 5 factorial, 7 factorial. And the third one is 1. So I'm just gonna write 1. I could write 7 factorial over 7 factorial 0 factorial. And on the bottom one, I'm like, how are these the same? This would be 20 factorial over 7 factorial 13 factorial. This would be 13 factorial over 5 factorial 8 factorial, and this would be 1. Are they the same? Do you see that the 12 factorials would cancel here? And in this one, the 13 factorials would cancel? And both of them would all end up being the same. In fact, it looks like a Mississippi question. And another way you could count this is you could take the students and line them up from shortest to tallest. And then in a hat, put 8 A's, 5 B's, and 7 C's and mix them up. And get everybody to pick out of the hat. And all the different words that could be spelled, and all those with the A, B's, and C's that you could spell would each be a different possible grouping. And so you could think of this as a Mississippi question with, oh, I shouldn't write it out because it's going to take me forever. 8 A's, 5 B's, 7 C's. Which, if all those letters were different, would normally be 20 factorial. But we have identical objects of 8 A's, 7 C's, and 5 B's. And you get the same answer that way. One of the crazy things about combinations, the same question can be logically thought about in different ways and can get you the right answer. The other crazy thing about combinations is sometimes you can think about it in a different way and actually get it wrong because you misunderstood something. And because the numbers are so big in the end, it's hard to tell if you are right or wrong. So, what I'm going to do, we'll do this question, and in the next question, I'm going to introduce you to your own brain, possibly making correct logical decisions, and possibly making incorrect logical decisions, and see if you can pick out the brains that are going right or going wrong. But first of all, in this one, if you wanted a poker hand that had no clubs, the easiest way to deal that would be to go through the deck, take out all the clubs. All right, here we go. Taking out all the clubs, I'm doing a good job. And then prepare to be amazed. I'm even going to shuffle. Okay, there we go. Let's see. 1, 2, 3, 4, 5. Did you get any clubs? No. How do you know? Check. Okay, don't tell everybody.
Sorry. Wow, I got 8 of spades, 6 of spades, jack of diamonds, 8 of diamonds, 6 of diamonds.
No clubs. Does this seem like a good strategy to guarantee that you'd have no clubs? So, does it make sense that the number of poker hands without clubs, if you took out the clubs and did every group of 5 from the 39 cards, you get 39, choose 5. And sometimes when you do combinations, pretty things happen. This is one of those pretty things. Look at this. There's a 39, man. Oops.
57.
You got it? Okay, thank you. Because I was writing on my calculator with pen. It's a pretty number. That's pretty. 575,757 poker hands have no clubs. And now, to make things interesting, for part B, we need to find the number of poker hands with no clubs. And at this point, I am going to provide you with three different solutions. I'm going to sell them like a salesperson, that they are all three completely correct. But they might all three be completely wrong. Or maybe two of them are right and one is wrong. Yeah, I kept three right, two wrong, that doesn't work. Or maybe just one of them is right. You have to decide. So here is what I'm going to do. I'm going to be salesperson, and this is correct solution number one. I want to have a poker hand with at least one club. So I've already nicely separated my clubs here. I have 13 of them. I mix them up. I choose one. 13, choose one. That's my first decision. Then after that, I take the other 12, put them back in the deck, shuffle it all up, and I take 4 more cards. How many cards are left in my deck? I've taken one out already, so there's only 51 left, and I choose 4 more. Could I get more than one club? Absolutely. Could I get all 5 clubs? Absolutely. Am I guaranteed at least one club? Absolutely. This is correct solution number 1. Okay? Now, club separate here. We're ready for correct solution number 2. I want to have at least one club, so I decide I think I'll use the knot strategy. The knot strategy says if I count all the poker hands and subtract the bad ones, I'll be left with the good ones. Well, all of them was 52 choose 5. We figured that out earlier. The bad ones would be the ones without any clubs, which was that pretty number, 57, 57, 57. So if I subtract the 39 choose 5, which is all of the poker hands without clubs, what would be left is all the poker hands with at least one club. Solution number 2. And correct solution number 3. I'm going to use cases. I've nicely separated my 13 clubs here, my rest of my cards here. So I'm going to break it up and say, well, at least one club could be exactly one club, count those ones separately. If I did exactly one club, case 1, one club, well, I go to my 13 cards, I choose 1, and from my 39 other cards, I choose 4 other ones. That would give me exactly one club. If I wanted to do 2 clubs, that'd be case 2, 2 clubs. Well, I have 13 clubs, I choose 2 of them, and then for my other 39 cards, I only have to choose 3 more. And this is a little bit long-winded, but I think you see where this strategy is going. To get at least one club, we have to do a third case with 3 clubs, which is 13, choose 3, and 39, choose 2. And case 4 would have 4 clubs. Wow, that's the ugliest club I've ever made. And that would be 13 clubs, choose 4 of them, and the 39 other cards, choose 1. And finally, case 5, choose all 5 clubs. So I go 13 cards and choose all 5 from there. And if I add those cases up, I would have every possibility of having at least one club. How did I do? I tried to present all 3 solutions that they were all correct. Maybe they are all correct. What do you think? Was I lying? Can you see how your brain would logically think any one of those 3 seems right? Okay? Logic over the years have been as follows. I've had students say, the last one is the most painful. Math is painful. Therefore, the last one must be the only one that's right. That's logic that I've gotten from some students over time. If we actually figure them out, okay, all 3 are not the same number. So that means something went wrong somewhere. We still got time. We still got like 3 minutes. Okay? I'm gonna just quickly do some math here to figure these out. Alright, here are the numbers results. 3, 2, 4, 8, 700, 2, 0, 2, 3, 2, 0, 3, and this one 2, 0, 2, 3, 2, 0, 3. Uh-oh. Those numbers tell us that they cannot all be right. They could still all be wrong. Or one is right and two are wrong. Or two are right and one is wrong. You should be able to tell me, based on math that we've done earlier today, which one for sure is wrong. Either the two are wrong or the other one is wrong. How can we say, based on the math we've already done, so we have to have at least one club? Well, in my argument, I tried to get at least one club in each one. Okay? Do you remember what this number was? The all number from before?
Yeah.
What was it? About 2.6 million?
Yeah.
So in poker, there are 2.6 million different hands, of which over 3 million of them have at least one club. This is bad. This is way too many. These ones are actually correct. The all minus bad, I think, is the best strategy. Now, why did our brain make us think the first one was right, but it was actually wrong? Well, there's actually a problem. If you have two decisions like we did here, and you could choose the same thing in either part, like in my 13 choose one, I could choose the ace of clubs, and then the 7 of clubs over here. But I could have chosen the 7 clubs first, and then chose the ace of clubs over here, and there's overlap. That overlap causes you to count things more impulsively. So if you're going to use two different decisions in combination, they cannot overlap. That's why the cases is fine, because the clubs and the other numbers are separate.